Am I audible?
Yes,
Yes,
completely
sir.
audible.
Okay, okay,
Yes, sir.
okay. Good evening, everybody. As a part of the now we are proceeding toward the end of this particular 1 week GAN course on the practical approaches to soil improvement and the sustainable geotechnical solutions. We have been hearing since last 5 days about the ground reinforcement, the technique to improve the capacity of the soil, and subsequently the sustainable geotechnical solution. Professor Pravir Kumar Ole have been delivering lecture over the last 5 days. So now toward the end of this particular 1 week GAN course, I'm going to give a small presentation here pertaining to the use of reinforcement on the embankment slope in the context of the pozzolanic material. So here the title of my presentation is the bearing capacity of the reinforced model embankment slope of fly ash and furnace slag. So here in this particular, I'm just going to give us a brief overview of this particular presentation in the beginning itself, and after that I will be dwelling on the presentation. So this particular presentation dwells on the strength evaluation of the geogrid and the rubber grid reinforced embankment slopes made up of two different pozzolanic waste material, that is the fly ash and the ground granulated blast furnace slag. The strength of the embankment slope was studied in terms of the bearing capacity response of the strip footing placed on the top of the slope through a small scale model test in the laboratory. These uh, tests were conducted through the variation of the parameters such as the location and embedment depth of the layer of the reinforcement considered in the study, location of footing relative to the slope crest and the thereafter slope angle. So on the basis of the critical slope angle and the optimum embedment depth of the reinforcement obtained from the investigation that was carried out on the geogrid reinforced flash slope, the study was further extended for the flash embankment slope reinforced with rubber grid, and thereafter ground granulated blast furnace slag embankment slope reinforced with geogrid as well as the rubber grid reinforcement. So the results obtained from the experimental investigations are presented in terms of bearing capacity improvement ratio, BCI ratio, and they further indicate that the several parameters studied have an important effect on the strength of the embankment slope. So the improvement in ultimate bearing capacity of the footing resting on top of either slopes, that is say the slope of fly ash and the slope made up of GGBS, is found to be is observed with the presence of the reinforcement. So in that case, the rubber grid reinforcement is found to perform better than the geogrid. Then this particular study demonstrate the utilization of the pozzolanic waste material like fly ash and ground granulated blast furnace slag as the fill materials in embankment, and subsequently the discarded tires as the reinforcing material in the most effective manner. So coming to the introduction, the industrial waste such as say fly ash and ground granulated blast furnace slag, which are the byproducts of the thermal power plant and the iron manufacturing industries respectively, they pose the main concern from the environmental pollution, and as such require the considerable area of land for their safe disposal. Then the structural fields or say highway embankment and geotechnical constructions are some of the potential areas which entails the large scale utilization of such type of waste material. Fly ash has been often used in the embankment and geotechnical construction. However, of late, the use of other industrial waste materials such as ground granulated blast furnace slag, copper slab, and so on, having pozzolanic properties, has also gained the much popularity in such type of construction, that is the construction of the embankment as well as some other geotechnical construction. Now on the other hand, the disposal of the discarded waste tires also poses the serious threat to the environment. The waste tires are nowadays being used in concrete and geotechnical construction. Similarly, they can be used in the embankment construction. Sometimes the foundations are required to be constructed either on the top of the slope field or on the slope itself. That is the foundation constructed on the sloping ground or hilly slopes, or the foundation of the bridge, abutment, etc. Under such type of circumstances or such type of eventualities, the bearing capacity of the footing may get reduced considerably based on the location of the footing with respect to the edge of the slope and thereafter the slope angle. So improvement in bearing capacity of such loaded slope is therefore a primary concern for the geotechnical engineers, because the structures resting on the slopes are liable to be unsafe in case of failure of slopes. So reinforcement of the slope field is one of the options to improve the bearing capacity. The considerable work has been seen on the behavior of the bearing capacity of footing on the embankment slope made up of soil. However, relatively less work is observed in the context of the embankments or slopes of fly ash and other pozzolanic materials such as GGBFS or say copper slag, etc. The studies which are carried out on the embankment slopes made up of other waste materials are also scanty when we compared it with the fly ash, because a lot of work has been done in the context of the embankment with fly ash as compared to other type of waste material, that is a pozzolanic waste material. So in view of this particular presentation is reporting the bearing capacity of the model strip footing on reinforced fly ash and GGBFS embankment. The effect of location of footing with three different edge distances was studied in the context of two different types of reinforcement, that is the conventional geogrid and thereafter the rubber grid, which was derived out of the discarded waste tires. The optimum parameters of the slope angles and embedment depth of reinforcement obtained from the reinforced fly ash was used in the reinforced GGBFS embankment slope. Coming to the materials now here. So, two waste materials, that is pozzolanic materials, namely say fly ash and granulated blast furnace slag, were used as the fill material. Apart from the conventional geogrid, sorry, the rubber grid derived from the discarded tires were also used as the reinforcement. Now, coming to the fly ash, this particular fly ash used in the study was procured from Eklare Thermal Power Plant, Nashik in Maharashtra. The geotechnical properties of the fly ash are shown in table number 1. Uh, the uh, the particles of fly ash were fairly well rounded and spherical in shape, with surfaces that appeared to be very smooth and non-plastic. Uh, we can see here figure 1 that indicates the SCM, that is scanning electron microscope graph for fly ash, and beside that the another figure is there which shows the same image of the GGBFS. So the grain size distribution of the fly ash is also shown here. Grain size distribution of fly ash is shown here. Grain size distribution of GGBFS is shown over here. And these are the chemical composition you can see from table 2 and table 3. They show the chemical composition of both the pozzolanic material. So far as this GGBFS is concerned, the GGBFS used in this particular study was made available by the JSW Cement Industry, Raigad, Maharashtra. We have already seen the same image of the GGBFS particle. We have seen the geotechnical properties of the this particular material GGBFS in table 1 itself, and thereafter chemical composition also we people have seen in table 3 for the GGBFS. Now coming to the particulars of the reinforcement here. So already I have mentioned that the two reinforcement we have tried here, geogrid and rubber grid. Basically, the objective was to examine the efficacy of the rubber grid, which otherwise would have been the waste material. So this rubber grid was derived from the discarded tire waste. So it was compared with the geogrid. Its performance was compared with the geogrid. It was the main objective. So uh, coming to the geogrid, so a commercially available polymeric coated polyester geogrid of 1 mm thickness was used in this particular investigation, which was made from this particular geogrid was made from high tenacity polypropylene rods, which are polymeric coated, different rib layout pattern give rise to different styles of unidirectional, bidirectional products. So here, bidirectional geogrid was used. So the dimensions of the aperture of the geogrid was 35 mm by 63 mm. Its tensile strength was measured as per the codal provision, and thereafter here you can see this particular geogrid in this particular figure. It indicates the geogrid used in this particular study. Now, coming to the rubber grid, so the rubber has got many excellent mechanical properties when compared with the other materials. So these include your important impact resistance, flexibility, abrasion resistance, and resistance to biodegradation. They make the rubber worthy, being a great engineering material like earth reinforcement. So in this particular in this particular investigation, the scrap tires were used for deriving the rubber grid, which could act as the reinforcement and which can replace the geogrid, that is the conventional grid reinforcement. So the rubber grid were derived manually from the sidewall and tread of the tire of heavy vehicles in the 5 mm thick string here, which you people can see in figure 6. So the rubber grids were formed in the size as that of the geogrid, because geogrid were formed means it was available in the size of 35 mm by 63 mm. So here this geogrid was also formed of the same dimensions with the help of the aluminum wire reinforcing strips were derived from the sidewall and tread of the tire. The strips of size of 5 by mm by 5 mm were cut from these parts. The size was restricted to 5 mm due to model testing and difficulties in the manual cutting. So here the properties of the rubber grid reinforcement is also available. They can be seen in table 5. Now, coming to the experimental setup and the procedure. So first of all, I'll discuss about the test tank and the loading frame. So figure 7 shows the schematic of the model test tank, and figure 8 shows the actual laboratory model test setup. So all the tests were performed in an open-ended model test tank. The inner the dimensions or that is planar dimensions of the tank were 2.4 meter by 0.31 meter, that is a 2400 mm by 310 mm with the depth of 900 mm. The aspect of the size and the zone of influence of the footing were also taken into consideration while deciding the dimensions of the model tank. The tank was fabricated considerably rigid so that the plane strain condition can be maintained throughout while conducting the experiment. So this particular test tank was provided with the horizontal sliding arrangement, the specially fabricated load device, oil pump, hydraulic jug, etc., with attached probing ring for the vertical load measurement. The roller adapter, that is 80 mm long and 70 mm in diameter, was aligned longitudinally on the model footing by sliding and fixing the position of the hydraulic jug on a loading frame. The calibrated probing ring of maximum capacity of 80 kilonewton was connected to the hydraulic jack with the mild steel extension rod here. The roller adapter was attached with the probing ring for applying the load on the model footing. The base of the loading frame, so designed, was fabricated and fixed in the laboratory with the concrete. The three sides of the model tank were prepared from 12 mm thick transparent perspex acrylic sheet, which was supported on 8 mm thick mild steel plate and angle column with nut bolt connections. So this was done to facilitate the easy visualization of the failure of the embankment on part of the observer. So here this particular figure 9, it shows the close-up of the experimental setup while measurements were in progress. Thereafter, this is about the strip model footing, the particulars of the strip model footing, a rigid model strip footing made up of the well seasoned solid of good quality of size 300 length, 100 width, and 100 depth was used for conducting the model test. A thin layer of the sand was glued to the base of the model footing using epoxy so as to render the base to be rough. It was done to ensure that the model footing will have freedom to adjust itself to any displaced position while the load continued to be applied gradually. The footing was placed on the embankment field uh, with the length of the footing running the full width of the tank. So this was done to ensure that the plane strain condition would be maintained throughout. And then the two ends of the footing plate were polished smooth for minimizing the effect of the end friction. Thereafter, you can see here the procedure for the preparation of the slope fill. The lubricant was applied on the inner faces of the tank so as to reduce the friction between the acrylic sheet and the filling material considered in the present investigation. The markings were done on the outside of these sheets at regular interval for meticulous development of the slope in layer. The filling material, may be fly ash, may be GGPF, was uniformly mixed with water. From a standard Proctor test, the fly ash was found to give maximum dry density with 20% of water content, and for GGPF 15%. The model fill slope made with the height of the 750 and it was compacted in 5 layer with each layer being 180 and it was compacted manually to 150 depth. The compaction was carried out using, as you can see from the slide, a 60 kg roller compacted with 30 tons for each layer. Now coming to the test procedure here. So after the compaction of the fill and covering the same with the weight gunny bags, for 24 hours the gunny bags were removed and the fills were cut with the sharp trowel to attain the designated slope. Then the upper surfaces of the fill was made perfect horizontal by trimming an extra soil, or means here the extra material. Soil means it is considered as a soil material, this fly ash or say GGBFS. And subsequently the model footing was placed at certain desired location from the edge of the slope. So vertical settlement of the footing was measured with the help of the two magnetic base dial gauges with certain list count and 50 capacity mounted on the ends of the model footing. The initial reading of the proving ring was set to 0. Similarly, initial observation of both the dial gauges were recorded before commencing the loading. The roller adapter with the proving ring was lowered and oriented axially just above the model footing with the help of the hydraulic jack. The load was applied gradually at the uniform rate. So each load increment was maintained constant around for 10 minutes so that the footing settlement in the slope will get stabilized. There, the proving ring reading and the dial gauge reading were recorded for each load increment, and from recorded load settlement reading, the pressure settlement curve was plotted. The ultimate bearing capacity of the footing was determined using double tangent method as suggested by Adams and Collins in 1997. The tests were repeated in order to get some degree of confidence with the limit of repeatability as 10% variation in the ultimate bearing capacity. Now, coming to the parametric study. So here, based on the findings of various researchers, the various uh, test parameters was taken for this particular investigation here, which are shown in table 6, which is there in the next slide. And here, figure 10, you people can see it is the geometry of the parameters for laboratory model test. So here, this is the model embankment. You people can see. Thereafter, here, this is the model footing. And D indicates the edge distance here, B is the width of the footing, LR is the length of the reinforcement, and Z is the depth of reinforcement here, or say reinforcement interval. And here, this is the slope angle. Here you people can see the various variables which was considered in this particular experimental investigation. Here, this particular slide is showing all those parameter. Basically, two filling materials were considered, that is the fly ash and GGBFS, uh, and three different types of tests were carried. Firstly, the test was carried out on reinforced fly ash slope. Second one was carried out, means the test was carried out on the fly ash slope only, but in that case, the single layer geogrid reinforcement was provided. And thirdly, the again the same slope, means the slope of fly ash material only, but here the reinforcement instead of geogrid, the reinforcement used was the rubber grid. And the constant parameter you people can see here, and the variable parameters you people can see. So far as the rubber grid reinforcement is concerned, for that only optimized parameter of Z by B and the critical angle, which proved to be 45 degree, uh, as observed from the experimental studies on the reinforced geogrid reinforced slope. So it was conducted, and edge distances were kept same, and similar analogy was followed for the GGBFS slope also. So in that case, unreinforced slope was carried. For the unreinforced slope, only 45-degree slope was considered, which proved to be critical one from the previous fly ash reinforced slope. And similarly here, edge distances were kept same. Edge distances 1 to 3, means D by B ratio here. And again, for the same optimized Z by B parameter, 0.9 and 1.2 here, the tests were carried out on blast furnace slope, which was made up of geogrid and subsequently of the rubber grid. So these are the various variables considered. Now coming to the results here, the main focus of the present study basically was to examine the efficacy of the geogrid and rubber grid reinforcement in improving the load carrying capacity of the slopes made up of two waste material, that is fly ash and GGBFS. So therefore, it is desirable to compare the response of the reinforced slope with the response of the footing on an unreinforced slope. So initially tests were conducted with the model footing of size 100 placed on the top of the unreinforced fly ash slope at three different edge distances from the slope crest for three slope angles and horizontal field considered in the investigation. To understand the effect of the slope angles on the pressure displacement response, the tests were conducted for all the three slope angles and compared with the horizontal field as compared in respect of the unreinforced fly ash parameter. For reinforced slope, the efficacy of the geograde layer of length 7B was investigated in terms of its depth of embedment, Z by D depth of embedment, that is 0.3, 0.6, 0.9, 1.2, 1.8, that is 1.8, 2.4, and 3. So, in case of reinforced fly slope, for each specific value of Z by the three tests were conducted by placing the footing at three different edge distances from the crest of the slope field. And pursuant to this, the efficacy of the rubber grid was studied in the context of the critical slope angle and the optimized embedment depth, that is say 0.9 and 1.2, as seen from the geogrid reinforced fly slope for all the three edge distances. Now, in the context of the GGBFS embankment, the investigation was carried out using geogrid as well as rubber grid for critical slope angle and the optimized embedment depth, that is a 0.9 and 1.2, and for all the three edge distances, that is D by B equal to 1, 2, and 3. And further, in order to express the bearing capacity with respect to the level surface, the investigation was also carried out with the horizontal field for the unreinforced embankment slope, fly ash, and GGBS. Now here we can see the here I have indicated the result graphically for the reinforced fly ash slope. So typical pressure settlement response in respect of the unreinforced fly ash embankment slope corresponding to all the slope angle, and unreinforced GGBS embankment corresponding to one slope angle of 45 degree is indicated here. The pressure settlement response you people can see here. So pressure settlement response characteristics for the unreinforced slope for D by B equal to 1, and the typical pressure settlement curve for the geogrid reinforced fly ash slopes in respect of the three slope angles and three edge distances corresponding to embedment depth ratio of 0.9 considered in this particular investigation are also indicated here in the figure. You can see 12A, B, and C. So the effect of the embedment depth ratio Z by B of single layer of geogrid reinforcement was examined by placing the layer of reinforcement within the fly ash fill at different depth, such as say Z equal to 0.3, 0.6, 0.9, 1.2, 1.8, 2.4, and 3, with three slope angles, that is 31 degree, 39 degree, and 45 degree. The bearing capacity improvement of footing on the reinforced slope is also represented by the non-dimensional parameter called bearing capacity improvement. The variation of the bearing capacity improvement with different embedment depth ratio for all the three locations of the footing with respect to the slope crest DE, and further for all the three slope angles considered in the present investigation is shown here in this particular figure 13. So from this particular figure, it is seen that the improvement in the bearing capacity of such slope depends upon the depth of the embedment of the reinforced layer and also on the distances. For all the slope angles under consideration, the bearing capacity improvement increases with the embedment depth Z by B up to certain critical value, and thereafter it decreases. It decreases with further increase in the embedment depth ratio. So, irrespective of the distance of the footing from the edge of the slope crest. So, it can be seen from this particular figure that the maximum value bearing capacity improvement is obtained when the ratio of embedment depth lies in the range of 0.9 to 1.2 in respect of almost all the cases of the reinforced fly ash slope considered in this particular investigation. So, this is an indication of the fact that the maximum improvement occurs when the embedment depth ratio Z by B ranges from 0.9 to 1.2, and in this range, the plastic failure zone of the slope is intercepted by the geogrid reinforcement layer, and the stress distribution is extended much below it. So this results in the spreading of the footing load onto a wider area beneath the reinforcement of the fly ash embankment, which is formed by relatively rigid region of the fly ash material and the reinforcement directly underneath the loaded area. So this deep footing effect basically leads to an improved load carrying capacity of the footing. Nevertheless, when the reinforcement is placed too close to footing, say Z by B less than 0.6, the overburden pressure on the reinforcement layer is inadequate to provide the necessary anchorage to the reinforcement against pull-out force, and due to this lack of confinement, the reinforcing effect of the geogrid, it cannot be fully developed. But when the value of the embedment depth ratio Z by B ranges between 0.9 to 1.2, the geogrid reinforcement causes much better load distribution over a larger area below the reinforced zone, and the adequate anchorage resistance can be fully mobilized under higher overburden pressure. So this improved load transfer mechanism result in the optimum utilization of the tensile strength of the reinforcement. Uh, Thereafter, further increase in the ratio of this particular embedment depth, that is Z by B. Beyond these values, it reduces the value of BCI, that is the bearing capacity improvement. So when the value of Z by B exceeds 1.2, the plastic failure zone doesn't extend below the reinforcement layer. The unreinforced zone immediately below the footing becomes thicker, thereby resulting into the possibility of the shear failure of the unreinforced zone, and this further decreases the load bearing capacity. So here, um, in case of the reinforced embankment slope, the maximum gain in the bearing capacity is obtained for a particular critical value of the ratio of the embedment depth. So we can note that at a shallow depth under the footing, both vertical as well as horizontal displacements are greater, and when the reinforcement is placed at such a depth where the mobilized lateral resistance for the soil displacement is highest, the maximum benefit in the improvement in bearing capacity can be obtained. So, with the increase in the depth of the layer of the reinforcement, lateral as well as vertical displacement in soil in the zone between the footing and the reinforcement layer also increases. As a result of this, the unreinforced zone is likely to fail in shear, thereby decreasing the load bearing capacity. The position the position of the geogrid layer at a depth greater than 1.8 to 2.4 b, means 1.8 to 2.4, does not lead to any considerable improvement in the load carrying capacity. So it is evident from the figure that we people have seen here. The location of the failure surface was established at the end of each test. The failure surface developed above the geogrid when the ratio of the embedment depth Z by B was greater than 1.2. The pressure, the pressure settlement characteristics we people have seen previously also indicate that wherever excessive settlement is the controlling factor in determining the allowable bearing capacity, incorporation of the geogrid reinforcement in the flyash embankment slope may reduce the settlement ratio considerably for the same pressure level. Thereafter, here in this particular table 7, we can see the percentage increase in the ultimate bearing capacity of the geogrid reinforced flyash slope for different Z by value and with respect to various edge distances. Thereafter, here uh, this particular figure 14 it shows the variation in BCI with edge distances for reinforced flyash slope here for different angle you people can see here 14 ABC. So from this particular results it can be observed that with the increase in the edge distances from 1B to 3B, the bearing capacity improvement is found to decrease here from 1.40 to 1.27, 1.43 to 1.31 and slope angle of 31 degree, 39 degree and thereafter 45 degree respective. The decrease in the slope angle, the bearing capacity improvement, BCI value increases. Here now we can see the figure 15 here. This 15 and 16 uh, figure 15 indicate the pressure settlement characteristics for the rubber grid reinforced flash slope here for the critical slope angle which was considered 45 degree, and thereafter figure 16 indicates the variation of BCI bearing capacity improvement with different values of DE by B for the flyash embankment slope here with different reinforcement. So here we people can see the performance of the rubber grid is superior as compared to the performance of the geogrid. So from this particular value here, uh, as I have already told you people that the performance of the rubber grid is means the performance of the rubber grid as compared to the geogrid when it is compared with the geogrid reinforcement, the former one, that is the rubber grid, is found to give the bearing capacity more than that of the geogrid, say in the range of around 10 to 13.9%, and thereafter 4.4 to 5%. So here the trend of variation of the bearing capacity improvement with the embedment depth with the edge distance in respect of rubber grid reinforced flyash slope is found to be similar to that which we people have seen in case of the geogrid reinforced flyash slope on the preceding slides. So further, when the effect of edge distance on the ultimate bearing capacity is studied in the context of the rubber grid reinforcement or rubber grid reinforced embankment slope, the trend similar to that seen in case of reinforced flyash slope is observed. So when the edge distance increases from 1B to 3B, the strength is found to increase by 16.2 to 14.4%, 16.2% and 14.4% corresponding to the value of Z by B, 0.9 and 1.2 respectively. Now, the better performance of this particular rubber grid, it may be attributed to the improved frictional adherence between the longitudinal members of the grid and the soil, which is influenced by the surface properties and coefficient of friction between them. The nylon belt that is provided within the tread and the sidewalls of the tire, it remains protruded even after stripping. So this protruded nylon belt, it creates the desired roughness in the rubber grid, which in turn develops the greater frictional resistance, even if its tensile strength of the rubber grid is considerably less as compared to that of the geogrid. And further, the semi-elastic properties of the rubber grid impart better pseudo cohesion due to the temporary deformation of the rubber grid. So it may be noted that the conventional geogrids lack in this particular mechanism. And moreover, because of the apertures present in the grid structure, there are chances for better interlocking of the subgrade and the reinforcement along with the backfill material. So all these factors make the rubber grid to perform better than that of the geogrid. Now, coming to the reinforced GGBFS this particular embankment here. So these are the pressure settlement characteristics we people can see in the figure 17 for geogrid and rubber grid reinforced slope. Of course, here also only critical slope was considered, which was deduced from the extensive study that was carried out on the flyash slope, reinforced flyash slope. So in this particular table, we people can see here the trend remains same as that which we people have seen in case of reinforced flyash embankment. Trend doesn't change. Only there may be change in the values. So this particular table, it shows the percentage increase in the bearing capacity of the geogrid and rubber grid reinforced flow here. So here also it is we people can say we people can find here the ultimate bearing capacity of the GGBFS embankment. It increases with the inclusion of either reinforcement geogrid as well as the rubber grid at both the embankment depth, that is say Z by B equal to 0.9 and 1.2. The bearing capacity was found to increase in the edge distance from crest of the slope. When compared with the unreinforced GGBFS embankment, the bearing capacity of the geogrid reinforced slope was found to increase in the range of 13 to 15 and 13 to 15% and 11.2 to say 12.20% for the embedment depth of 0.9 and 1.2. The bearing capacity uh, is found to be slightly on a higher side for the embedment depth or embedment depth ratio Z by B of 0.9 as compared to that observed for the embedment depth ratio Z by B of 1.2. Similarly, the bearing capacity of the rubber grid reinforced slope was found to increase in the range of 20%, 20.3% say to 36.5% and 39 to 40% respectively, corresponding to the embedment depth of say 0.9 and 1.2 respectively when compared with the unreinforced GGBS embankment. So further, the bearing capacity is found to be slightly on higher side for the embedment depth of 1.2 as compared to that observed for the embedment depth ratio of 0.9. When the variation in the bearing capacity for both the types of reinforcement, that is geogrid and rubber grid used in this particular study, it was seen that the bearing capacity was on higher side in case of the rubber grid for both the values of the embedment depth ratio, that is Z by B 0.9 as well as 1.2. The increase being in the range of say 6.4 to 18.8% and 24 to around 26%. So this particular trend is similar to that seen in respect of the rubber bead reinforced flyash embankment slope. Lastly, geogrid reinforced horizontal fill. So few results I am presenting over here. The results obtained in view of the limited experimental investigation that was carried out in respect of the reinforced and geogrid reinforced horizontal fill made up of the fly ash and GGBFS respectively, they are presented in this particular table. Uh, the values of the bearing capacity of the unreinforced fly ash and GGBFS horizontal embankment fill and embankment slope uh, here embankment slope of 45 degree with respect to edge distance of 3b are presented in this particular table. Similarly, the values of the bearing capacity of the geogrid reinforced horizontal fill of fly ash and GGBFS with respect to Z by B equal to 0.3 are also given. So when the bearing capacity of the unreinforced fly ash and the GGBFS horizontal fill is compared with the unreinforced fly ash and GGBFS embankment slope, the bearing capacity of the horizontal fill is found to be on higher side uh, by say 71.4% and 46% respectively with respect to the embankment slopes. Similarly, for the geogrid reinforced flash horizontal fill with layer of reinforcement placed at Z equal to 0.3b, the bearing capacity was found to be with respect to horizontal fill was observed to be around say 124 more than the geogrid reinforced flash slope. So when the unreinforced horizontal flash fill is compared with the geogrid reinforced horizontal flash fill, the bearing capacity of the former one is found to be on higher side, say by around 37% here, and the corresponding increase in case of geogrid reinforced horizontal GGBFS embankment fill was found to be 18.5%. So now, while summarizing here, summarizing the results,
Might have network problem. I think meeting is disconnected.
Just 1 minute, everyone. There is some technical glitch.
Okay, okay.
Am I audible?
Yes, sir. Yes, sir.
हाँ या बोला किसी ने.
Yes, sir, your sound is coming. You can start. Share the screen.
Am I audible?
Yes, sir, you are. PPT is also seen.
Okay, thank you. So I think I was discussing about I was summarizing the findings of this particular experimental investigation here. uh, Here, on the basis of the result that I have discussed, now I'm going to summarize the findings in a nutshell. So, means in briefly, the embankment made up of the industrial waste material such as fly ash and GGBFS, it can be provided with the steeper slope than the angle of internal friction of the fly ash and GGBFS. The inclusion of both the types of the reinforcing material, that is geogrid and rubber grid, at suitable location within the slope field significantly enhances the capacity of the footing on such slopes. The optimum benefits are likely corresponding to the embedment depth ratio of 0.9 and 1.2, so far as this particular investigation is concerned, and so far as the parameters which we have considered. The bearing capacity of the footing decreases with the increase in the slope angle for the unreinforced and reinforced fly ash embankment slope. The decrease being in the range of 1.3 to 29.5% and zero point 0.9 to 15.9% in case of the unreinforced and geogrid reinforced fly ash embankment slope. The age distance is found to be one of the important influencing factor on the load carrying capacity of the slopes, and in general the bearing capacity increases with the increase in the edge distance irrespective of the unreinforced and reinforced embankment, and further irrespective of the material. So the increase is in the range of say 31 to 80% and 49 to 89% in case of the geogrid and rubber grid reinforced fly ash slope. The corresponding increase in case of the geogrid and rubber grid reinforced GGBFS embankment was found to be in the range of 11.6 to around 14.9% and thereafter 20.3 to 40% respectively. The bearing capacity the bearing capacity improvement initially increases with the increase in the embedment depth ratio up to 1.2 and thereafter decreases irrespective of the edge distance and the slope angle in case of the geogrid reinforced fly ash slope. So it seems that the reinforcement at a depth greater than 1.8 times the width of the footing doesn't improve the load carrying capacity, and notwithstanding the BCI values, uh, they show the reduction in magnitude with the edge distance for the given embedment depth ratio. when compared with the performance of embankment slopes made up of two different waste material, that is a fly ash and GGBFS, considered in the present investigation with respect to the critical slope angle and other common parameters such as edge distance and embedment depth ratio, the strength of the embankment slope made up of fly ash is found to be on higher side. So, when compared on the basis of the performance of two different types of reinforcement, that is geogrid and rubber grid, the rubber grid was found to perform better than the geogrid. So when the rubber grid was used as the reinforcement at optimum embedment depth ratio, the ultimate bearing capacity was found to be on higher side in case of fly ash and GGBFS embankment respectively. Thereafter, when the load carrying capacity of the unreinforced fly ash and the GGBFS horizontal fill was compared with the embankment slope of the same material, here the capacity of the horizontal fill was found to be on higher side. It is obvious also by 71.4 and 46% respectively. The strength of the geogrid reinforced horizontal fill, that is fly ash and GGBFS, was found to be on higher side here by 18.5% to 36.75% as compared to the unreinforced horizontal fill. So here, pursuant to the aforementioned conclusions, the load carrying capacity of the embankment slope made up of two different materials used in the present investigation depends upon the various parameters such as the slope angle, edge distance, location of the reinforcement within the slope field. The investigation confirmed the effective utilization of the industrial waste materials such as fly ash and GGBFS as the fill material here, and the discarded waste tire as the reinforcing material for their bulk utilization in the geotechnical applications, particularly for the road and rail embankment. So here, with this, this is the end of the presentation. The objective was not to provide basically the research result or all those things. I just wanted to demonstrate how this particular fly ash and GGBFS can be used as the potential material as a part of substitute to the natural soil here for the application in field or say embankment. And thereafter we are talking about the conventional reinforcement. Suppose here I was concentrating only on geogrid reinforcement, so it is a polymeric reinforcement. On the other hand, we people are facing, or say all over the world, the problem of the disposal of the discarded waste tires is being faced. So here the objective was to demonstrate how we people can effectively use the discarded waste tire, how we people can uh, convert those discarded waste tire in the sort of reinforcement at par of the geogrid reinforcement. And here we people can see the results are quite encouraging. So it can pave the way for the further research in this particular direction. Here only I was discussing about the utilization of such type of waste material, and especially the use of discarded waste tire as a sort of reinforcement in the embankment. But similar sort of thing we people can do in the road pavements also. So with this I conclude my presentation. This was the last presentation, and we are coming towards the
Thank you, sir.
we are coming toward the end of this particular thing. So I think my students have already, the student coordinators have already informed that tomorrow there will be an examination. Vipin,
Yes, sir.
what time examination will be there?
Sir, we will inform the time in the WhatsApp group.
Okay.
Yes, sir. Okay, thank you, sir. So on the behalf of organizing committee, we extend our deepest gratitude for all the participants for your commitment and for making this course a truly memorable and impactful event. We wish you all the best in the future. Thank you. And about the tomorrow examination, we will inform in the WhatsApp group. Thank you. Good night.
Thank you.